Okay, so let's start with the expiration activity. So it says a change in an object's motion is related to both force and how the forces act. How long refers to time. Remember, force multiplied by time is called impulse, but how long doesn't always equal time, it can be distance as well. When considering the quantity force multiplied by distance, it is called work. So we're going to be figuring out work. Work is done when an object is lifted up against Earth's gravity. The heavier the object, or the higher it is lifted, the more work that is done. The amount of work done is dependent on two things, the application of a force and the movement of an object. When the movement of the object is in the same direction as the force, the amount of work is calculated with the following equation. So when you're calculating work, you take force times distance. And force is going to be in newtons and distance is in meters. So that's what we measure with this scale here. We're measuring force in newtons. And then the other equation says the definition of work states nothing about how much time it takes to do the work. When carrying an object up some stairs, you do the same amount of work whether you walk or run up the stairs. So why are you more tired after running upstairs in a few seconds than after walking upstairs in a few minutes? To understand this difference, you must first understand how fast the work is done. So power equals the amount of work done divided by the time it took to do the work. So we take power equals work, which we calculated here, divided by time. So that's different than work. Because you'll notice, like, when you run upstairs, you get tired as opposed to walking upstairs. You might not get as tired. Okay. So, a truck exerts 2,700 newtons of force on a car that is stuck in the mud and does not move. How much work has the truck performed? So, which equation would we use on the first side? Would we use the first one or the second one? Right. So work equals force times distance. So what is our force in this problem that they're giving us? Yeah, 2,700. So work equals 2,700 newtons. And then what is our distance in this equation?
Sorry.
I'm sorry? What is our distance in this equation? It says that the truck is stuck in the mud and does not move. So is it moving at all? Is there any distance? No. 0. So if you have 2,700 newtons times 0, what does that equal? Well, if you multiply anything by 0, what does it equal?
The same numbers multiplied by,
Right? No, that's if you multiply by 1.
oh, okay, then, 0.
0, right. So there is 0 work being done in this equation because the truck isn't moving. So it's just sitting there.
I'm sorry, I got confused.
Oh, that's fine.
0 and 1.
Yeah, so if you want to write that down. Anytime you're not moving at all, you can't be doing any work. Okay, and our second one says if 2 joules of work is done in raising an apple 8 meters, how much force was exerted? So this is a little different. We're going to have to rearrange the equation. So we want to calculate force. So would we use the first or the second equation? Well, look at what the equations are made of first. We are trying to calculate force. Which one do you think we could use to do that? Yeah. So we're going to have to do a little bit of rearranging. You have to think back to some algebra for a second. So our normal equation is W equals F times E. So we want force to be on that side. So do you know how I would do that? how I would rearrange to put F on the left side of the equation?
I do not.
Okay. Well, you could start off by getting rid of the W. So you could start off by dividing both sides by W, which would get rid of the W on that side. But now, all we have to do is move the F to this side, because we want it over there. So this crosses out. Our next one would be F equals D over W. And that's it. That's how you would rearrange it. So I just divided each side by W and F over there. So now we got the equation right. Now we just have to plug in the numbers. So let's look back at our problem. If 2 joules of work is done in raising an apple 8 meters, how much force was exerted? So which one is our distance?
8 meters.
So we got F equals 8 meters over what?
2 joules.
Yep, 2 joules. Okay, so F equals what? 8 divided by 2, what's that? You don't 8 divided by 2?
No, I can't do that in my head.
Okay. That's okay.
Just,
Here, let me grab you a calculator real quick. There you go.
Did you print it? Just go to the print and you should see HP desk. Should be the printer. Let me see.
0.32.
Yeah, should go to that. And
8 divided by 2.
laser jet.
Yeah, so just do 8 divided by 2. Yep. So our force equals 4. And then what are our units for force? If you look on the first page, what should force be in?
Force.
Newtons, right? 4 newtons. But always remember when you're writing your answers to include the units. Otherwise, you don't really know what you're doing. If I were to just pick it up, I wouldn't know what I was looking at. Okay? Does that make sense?
Yeah.
Okay. So there's the first 2. Alright, so next, number 3. A weightlifter lifts a set of weights a vertical distance of 2 meters. If a constant net force of 350 newtons is exerted on the weights, what is the amount of work done on the weights? So again, which equation would be used for this one? We want to calculate work. First one. Okay, so we're using this guy again. Okay, and we don't have to rearrange it because we want to calculate work. So which one would be our force? Which number in this equation would be our force?
350.
So we have W equals 350 newtons times what would be our distance?
2 meters.
2 meters. So 350 times 2 meters. Now what does that give us?
700.
Right. So the amount of work done for that weightlifter would be 700 joules. Now you'll want to remember that number for the next problem because it says if the weightlifter in the previous question takes a total of 2 seconds to lift the weights, how much power is performed? So we want to calculate power. Which equation would we use now?
The second one.
The second one, right. So now we're plugging in P equals W over delta T. So what would be our work in this equation? The amount of work the weightlifter did.
700.
So P equals 700 joules. And then what would be our time?
2.
Right, over 2 seconds. And what does that give us?
350.
350 watts. So that's how much power it would take to perform that. Does that make sense?
Yeah.
Awesome. All right. So now let's move on to the work and power lab on page 12. So supplies we need. We have a ramp. We have our cart, stopwatch. We're going to need books. So let's grab some textbooks real quick. We'll use these ones because they're not big, terribly big, but they're big enough. And a tape measure. And our spring scale is right there. Okay. So the first thing we want to do is attach these. So let's attach our cart to here. Let's see. Cart of course spring scale. So attach our cart to here. And it says elevate one end of the board with the thickness of one book. So let's put one book down and then put your board on there. Just kind of set it like this. Yeah, you kind of want to make a ramp. Sorry. No, you're fine. Okay, and then you want to pull the cart up the board with the spring scale parallel to the board. Keep the movement as slow as possible. Let's see here. Let's try pulling our cart up the board and see what kind of a measurement that gives us. Okay, look on here now while you're doing it and see how many newtons it is. Set it right here. Now pull.
That's all.
Okay, that's fine. Okay, read the spring scale on the cart and record this in table 1. So you're going to want to record it in this table. So we're just doing one book right now. So you'll want to put the force right there.
And that was
Yep.
0.
0.1 at least. And we want to measure the height of the board. So, go ahead and measure the height of the board at the book.
Inches, right? Or
Centimeters. You'll want centimeters. Okay, and then record that for your height of the ramp. So see above the table it says height of the ramp with one book. Okay, and then next measure the distance from here to where you pulled the cart. So you pulled it all the way onto the book, right? Yeah, so measure how far that is.
Like about, or just start from right here? Or
Yeah,
about-
that's fine. You just stopped about there. About 37? Sure. So that will be the distance the cart is pulled for that one. Okay? Alright, so next, measure the distance. Okay, we did that. Place 2 books under the board, and this time measure the distance the cart travels to the same height found in step 4. So let's add another book. There. Okay, and you're going to measure the force again. So pull the cart up the ramp again. And, just pull it at like a steady rate so that way you can get a good reading. So don't be afraid to pull too fast. Okay. That's good. Okay, now we're going to, it says place 2 books under the board. This time measure the distance the cart travels to the same height found in step 4. So what was the height? 4? Yeah. So the height is about right here. So we need to measure the distance from here to here. So I'll hold my finger here, and if you want to measure the distance there.
From here?
Mm-hmm. About 9 centimeters. Okay.
And that goes,
That will go. Because we're keeping 2 books up this brings doesn't tell us where to. Measure the height and then move forward. This height will be constant throughout the activity. Measure the distance the cart travels and record this in data. Place 2 books under the board. This time measure the distance the cart travels to the same height. Read the spring scale as you pull the cart and record this number in table 1. Well, let's.
Should I write it on the side somewhere?
Yeah, write it off to the side. We'll come back to it because it doesn't say exactly where we're supposed to record it. All right. Shorter. So just. Okay. So now we're going to measure the distance from here to here. So see if that's any different than our first trial. $37, same thing? Okay. So why don't you put that number right there in that column right there. Okay. So now we're going to, you got your distance and you got your force, now we're going to calculate the work done. So you just need to multiply this times that. Here is your calculator. Okay, and then record that in the 3rd column. And then do it again for the 2nd one. Okay. So what do you observe about the numbers in the last column? What does it signify? So what kind of numbers did we get?
The high numbers and low numbers.
Okay, So did it take more work to go all the way up the ramp or halfway up the ramp? Yeah, so it looks like when we pulled the cart to here, it was like half as much work as when we pulled it all the way up. Even though technically this was the same height, it still took more work. Why do you think it took more work here than when we had 2 books?
It's higher now. So
It's higher now, but we went to the same height. So why was it more work when we had it lower? What's different about how far we pulled it? So how far did we pull it the first time? You pulled it all the way, right?
Yeah.
And then how far did we pull it the second time?
About half.
About half. So the distance mattered, right?
Yeah.
So how far we pulled it, the further we pulled it, the more work it took. But the shorter distance, even though it was the same height, it was less work. Does that make sense?
No.
Okay, so that's the